is I think it's Denis Matignon, maybe, or Ghislain Haine. I don't know, but
okay, it's a video by Ghislain Haine.
By Ghislain. Okay, so it's Ghislain Haine from the Université de Toulouse, and the title is Structure Preserving Discretization of a Coupled Heat Wave Systems as Interconnected portHamiltonian Systems. So please launch the video.
Thank you for watching this video. My name is Ghislain Haine, and this is a joint work with Denis Matignon from ISAE Superior. We will talk about the structure preserving discretization of a coupled heat wave system. So first I will introduce the main objective and the definition and notation used in this presentation. Then I will present the model studied by Zhang and Zhuozhuo. We will apply the partitioned finite element method, that is a structure preserving finite element method. We will end with a numerical simulation to validate our result and conclude this work. So the objective is to simulate a coupled heat wave system and investigate the long-time behavior proved by Zhang and Zhuozhuo. To do so, we will use a finite element method because it allows for complex geometry, and we have access to a wide range of implementation tools. We will work in the framework of portHamiltonian system, since it models energy exchange between simpler open subsystems. So here, the open heat equation and the wave heat equation. And because it encodes the power balance in a Stokes-Dirac structure that is preserved and translated into a Dirac structure of the discrete level, the partitioned finite element method, such that the discrete Hamiltonian satisfies a power balance that mimics perfectly the continuous one. We are working in the linear portHamiltonian framework, so the Hamiltonian is a quadratic functional of the energy variable alpha. The co-energy variables, as usual, is defined as a variational derivative of H with respect to the energy variables. We have a constitutive operator, which is linear and positive definite, which relates the co-energy variables with the energy variables. So the existence of Q is due to the fact that H is quadratic. We have a structure operator J, which is linear and formally skew-symmetric, a resistive operator R, which can be decomposed like this with S positive definite. We have a control operator B, which allows to append the system with an input U and a collocated output Y. We are working with this kind of equation, which is a portHamiltonian system written in co-energy formulation. That is, there is only E appearing in the equation. So it takes into account the constitutive relation given by Q on the left and S here. So the Hamiltonian along this solution satisfies the lossy power balance. Since R is positive, this is indeed signed, and with the minus, we have that the variation in time of the Hamiltonian along the solution is less than the power supplied to the system. We now present the simplified linearized fluid structure model studied in the paper of Zhang and Zhuozhuo. So there are three kinds of configuration. The heat equation satisfied by the temperature T is on the domain omega-1. The wave equation is on the domain omega-2. The transmission says that the velocity of the membrane is equal to the temperature at the interface, and that the flux is equal at the interface. And of course, we have to add some initial data. We also need a geometric control condition to analyze which type of decay will be satisfied by the Hamiltonian. So it only says that every characteristic lying in the wave domain have to meet its domain in finite time. So in their paper, Zhang and Zuazua prove that this system is well posed. And what is our main concern here is how the solution behaves at the infinity. The rate of decay is never exponential nor uniform, so it depends on the geometry and on the initial data. If the geometric control connection holds, the decay will be polynomial, and if the geometric condition fails, it will be only logarithmic. In our simulation, the initial data are such that the constant solution here is always 0. So in the paper of Zhang and Zuazua, the fluid is approximated, is modelized by the heat equation, and the Hamiltonian is given by this classical quadratic functional. The energy and co-energy variables are both the temperature. The resistive port are given by minus the gradient of the temperature and the heat flux. And the constitutive relation that is used to relate these two quantities is the Fourier's law, with PHS formulation in co-energy formulation is given by this equation. And the boundary port make appear the part gamma 1 and the interface. So at the interface, we want minus the heat flux, and we have the Dirichlet boundary condition on gamma 1. Then we have this lossy power balance, which is well known for this trivial parabolic system. The structure is approximated by the wave equation, and the Hamiltonian is given by the sum of the kinetic energy and the potential energy of the membrane. The co-energy variables are the same, that is the velocity and the stress. And the co-energy formulation of the portHamiltonian system is given by this equality. So we recover divergence and gradient, but we do not have the minus as for the heat equation. The boundary port again makes appear the interface and the other part of the boundary for the wave domain, that is gamma 2. We control the velocity of the membrane, and we observe its deformation. And the Dirichlet boundary condition of the membrane has been rewritten as a Dirichlet boundary condition, but for the velocity. And we obtain this lossless power balance that is very classical for hyperbolic system. Now we want to couple these two equations written as a portHamiltonian system, and we use a generator interconnection on the interface, which says that the input of the heat equation is minus the output of the wave equation, and that the input of the wave equation is the output of the heat equation on the interface. So the total Hamiltonian is the sum of the two Hamiltonian, that is the one for the heat equation and the one for the wave equation. And the dissipative power balance is given by the heat flux on gamma 1. Now we will discretize this system using the partitioned finite element method, which is structure preserving. So we will, on the one hand, discretize the heat equation, on the other hand, discretize the wave equation, and finally, discretize the generator interconnection. So the partitioned finite element method relies on three steps. First, we write a weak formulation, we perform a Stokes identity on some line, and finally, we apply the finite element method. So this is strongly related to the mixed finite element method. For the heat equations, weak formulation write like this. For the wave equation like this, so we see here minus div minus grad, here div and grad. And the Girard interconnection is simply this equality. Now we apply green identities to make appear the boundary term of interest. So integrating by part the first line on the heat equation makes appear the control U1 at the interface, and the output on the other part of the boundary of the heat domain. Applying the same green identity to the second line for the wave equation make appear the control U2 at the interface and the Dirichlet boundary condition on gamma 2. And we do nothing to the Girard interconnection. There is something that has to be noted in this weak formulation. We do not make appear the Dirichlet boundary condition on the temperature, but the observation of the heat flux on gamma 1. In fact, this observation is exactly the Lagrange multiplier of this Dirichlet boundary condition on gamma 1. So indeed, in this way, we will be able to impose the wanted Dirichlet boundary condition. Now we project our system on finite element basis. So Xi int will be the same for the two systems on the interface, and on the domain and the other part of the boundary, gamma 1 and gamma 2, each system will have their own finite element basis. So projecting the heat equation, the weak formulation of the heat equation, we obtain this algebraic structure. On the left-hand side, you have a block diagonal matrix given by the classical mass matrices of these finite element families. And on the right-hand side, you obtain a very sparse skew-symmetric matrix, where D1 is given by the gradient. For the wave equation, we also do the same. We obtain again on the left-hand side block diagonal mass matrices. We obtain again skew-symmetric sparse matrix on the right-hand side. And of course, for the Girard operator, we only obtain this simple equality. Now defining this matrix C as a Girard interconnection matrix, we can rewrite everything with this big block. And finally, the discrete Hamiltonian, defined as a continuous one evaluated in the approximated solution, satisfies this discrete lossy power balance, which says that the variation in time along the solution is exactly given by minus the heat flux square. So this mimics perfectly the continuous power balance. Now we perform some simulation to check if indeed we recover the decay rate proved by Zhang and Zuazua. So we consider these two domains. In the first part, we are in the case where the interface is inside the whole domain, and we will look either the heat equation at the outside and the wave inside and the other way. And this, in this L-shaped case, either the heat equation is on the L, either the wave is on the L. So we have the four cases mentioned at the beginning of the presentation. We obtain this kind of Hamiltonian versus time, so in log-log scale. When gamma 2 is empty, we obtain this blue line. So since gamma 2 is empty, it means that the wave equation is inside and surrounded by the heat equation. So it must be damped, but there is another damping. So Zhang and Zuazua proves that it has to be polynomial in a long time, and this is exactly what we obtained. And in the case where gamma 1 is empty, so that when the wave is outside, there is whispering galleries appearing, so trap rays, and the decay must be logarithmic, and this is what we obtain also. In the L-shaped case, again, we have the logarithmic case when the GCC fails, and a polynomial decay when the GCC holds. Now I will show some video. So this is a case where we have the wave inside the domain. So we see the polynomial decay to 0. Here we are in the case where there is whispering galleries. So some part of the wave equation will continue to turn around its domain. As you can see, the decay is very slower than in the previous case, so logarithmic. And we can see appear the whispering gallery, that is a trap rays that turns around its domain. Now we are in the case of the L shape. So here the GCC holds, since the wave equation, the characteristic of the wave equation will always encounter its domain. So the decay is polynomial. We are in the case where the GCC fails. So there is always wave traveling in this way and in this way, and never encounters its domain. And the decay is only logarithmic. Okay, to sum up, we perform a numerical validation of the long-time behavior of the heat wave system studied by Zhang and Zhuozhuo. Now, to go further, the choice for the finite element families should be analyzed for an optimal choice between computation time and order of convergence. We should also work on symplectic time scheme, but the difficulty here is that the heat equation have an algebraic constraint, so we are in the case of differential algebraic equation. And finally, we could, since we are interested only in the power balance, we could look at model structure preserving model reduction to reduce the number of degrees of freedom inside the domain. Thank you for your attention.
Thank you very much, Ghislain. Are there some questions from the room?
I'm the co-author, so I can answer the questions, if any, in the room. No question? On the chat, there are some questions.
Well, I have a question for Ghislain. It's in some sense related with your further work. In your numerical simulation, you couple the discretization of portHamiltonian subsystems. But I would like to know if at any time the geometrical structure of this type of systems is used. For instance, using some direct structures like in the works of Van der Schaaf and collaborators. That is related with this symplectic scheme that you propose to investigate further.
Denis, do you have an idea?
Your question is about the work of Haine
Yes,
van
about
der
the work
Schaaf?
of Ghislain,
Yeah.
about this, if he is planning to use some geometric descriptions of portHamiltonian systems, for instance, in the works by Van der Schaaf, for instance.
Haine van der Schaaf and co-authors,
Yes.
especially Goran Golo, they first discretized portHamiltonian system in 2001, I think, but it was only for the wave equation in 1D and something which is close to the finite difference scheme on staggered grid. And since then, there are not many works on the numerical side which do preserve the Stokes-Dirac structure for the infinite dimensional portHamiltonian system into a Dirac structure at the finite level. They know how to do this from the physics of Goran Golo in dimension 1, and the vibrating string with constant coefficient and so on. So the idea of the partitioned finite element method that we introduced with Ghislain, with Laurent Lefebvre in Valence, and also Flavio Ribeiro Cardoso in ITA in Brazil, is to extend to the higher dimension. So here, all the example, all the simulation which have been run by Ghislain are in dimension 2. We also have result in dimension 3, and it is structure preserving, but we do work in the framework of a portHamiltonian system.
Maybe I can just add the fact that so I share my screen. Here you can you have the direct structure as the graph of this skew symmetric matrix. So this is the interconnection matrix, but you have to modify the scalar product with this mass matrices, and you recover exactly the Dirac structure at the discrete level.
Thank you very much. It's very interesting. Thank you very much. Are there more questions from the room or in the? So, if not, thank you very much again to the speaker. Thank you very much, Ghislain. So I will pass the chair to my colleague Alessandro Bravetti from Mexico. Alessandro, please.
Thank you. Thank you. So our next speaker is Pablo Suarez Cerrato. He's a professor at the National Autonomous University of Mexico, and he will present examples of symbolic and computational and numerical computation in Poisson geometry. So I guess we can now see the video. And just to remind